Hi everyone, this is Mr. N again, and today we're going to work on our other chapter 4.1. Let's indicate that this is 4.1 to 4.4 review. This is our second extra review. And let's go ahead and take a look at this first problem. This first problem says the figure below shows that the graph of f prime, the derivative of the function of f on the closed interval from -5 to 5. The graph of f prime has horizontal tangent lines at x equals -4. So we've got horizontal tangent lines here at x equals -4. So I know that this is a horizontal tangent. And at x equals -1, at -1, I've got a horizontal tangent there as well. Let's do this in another color since the graph already is blue. And then I've got at x equals 2, I've got another horizontal tangent, and x equals 4. So this graph should probably be shifted over just a little bit here to, let's go ahead and fix that on our, didn't look so good. So right there is really what it should look like. Okay, and the function is twice differentiable, with f of -3 being equal to 5. Okay, so the first thing and foremost thing that we need to understand is that we are looking at an f prime graph. As it says, the graph of f prime. So, so this is a derivative graph that we are taking a look at here. So one thing we know is that all these horizontal tangents are going to be our zeros for f double prime. So let's make sure we understand and clarify that. Now, one thing to note is I can get intervals of increasing, decreasing right away because I have an f prime graph. I know the zeros on this f prime graph. So since I know those zeros, let's go ahead and quickly outline some of those. And let me go ahead and use a different color again so that we can see what these zeros are. And I've got a zero right here. And if I put this on a number line, it'll help us. Let's go ahead and do a different color for this one, and then we'll use this. Okay, so I've got a 0 at -5. I've got another 0 right here at 3, at -3. I've got another 0 right here at 2, and I've got yet another 0 right here at 5. So this is my f prime graph, and just based on this, before I even do anything, I'm given a lot of information here. I can determine that anything between -5 and -3 right here, between -5 and -3, it's above the axes. So all of these are positive values. Now I don't need to go beyond -5 to the left of it or to the right of 5 because here is my interval from -5 to 5. I'm only concerned with that. So back to this, we look from -5 to -3. I've got all positive values, so I'm going to indicate that these slopes are positive. Here, I will indicate that these slopes are negative, from -3 to +2, because again, all of these are below the axes. And now I could do one more thing here. In this interval from 2 to 5, I will go ahead and indicate that these slopes, again, remain negative. So let's take a look at what questions were asked, and we will base what we have here. Right away, you should see something. You should see that there is a maximum. This is where the interval, it changes from increasing to decreasing. It changes. So I do have a maximum at this point because, again, I've got a positive slope to a negative slope. I'm looking at an f prime graph, so I end up with a relative maximum right there. So let's see what it says, and then we'll justify and answer all these questions. So for the first one, find the x-coordinate of each local minimum or maximum of the graph of f and justify your answer. Well, we just drew our line graph here for the f prime, so we know that there's no relative minimum, but I do have a relative maximum. So no relative minimum and a relative maximum at, this will be x equals -3. And this is because we change from increasing to decreasing. So in other words, the slopes change. The slopes of the tangents change. So that's our justification for this. All right, let's move on to the next one. I will slide this up a little bit more. Find the x-coordinate of each of the points of inflection of the graph of f and justify your answer. So for points of inflection, I need to examine the second derivative. So that's where these horizontal tangents on this f prime graph come into play. So I need these zeros because these will give me the possible points of inflection. So I need where it's 0 or undefined. So let's list those. So f double prime equals 0 at the horizontal tangents of f prime. And this happens and yields possible points of inflection, or you can call them inflection points like that, at x equals, now this first one right here occurs at -4, then the next one occurs at -1 right here, and then the next one occurs at 2, and the next one we said will occur at 4 because in the problem they told us that is where the horizontal tangent is. So we're going to go ahead and say that this occurs at -4, -1, 2, and 4. These are possible points of inflection. How do I know if they are going to be points of inflection? I need to test them. So let's go ahead and test them again on we'll draw this in a black color here, on a f double prime number line. And I'm going to put my values here. And this is -4, -1, 2, and 4. And what I'm doing on this is to make sure to see what is changing in concavity, because if there's a change in concavity, I will have an inflection point. So let's test interval that is less than -4. So let's test a value less than -4, and when I test it in my f double prime, I'm going to take a look at this right here. These slopes are positive because this is my f prime graph. I want to take for f double prime, I need the slopes of that. These slopes are positive up to -4, so I will go ahead and indicate that these slopes are positive. Then I can test the next one right in here. In this region, these slopes are negative, so I have negatives. And then the next region will give me positive slopes, and then the next region again will give me negatives right here. And then finally, when I'm greater than 4, I will have positive slopes again. So we can see that there is a concavity change. So we have points of inflection. So our inflection points are at x equals -4, because I do have a change here in concavity. -1, I do have a change there, 2, and 4. So all those end up being inflection points because I have a change in concavity. And that's my reasoning for that. Okay, let's go ahead and move on to the next question, and I'm going to go ahead and slide this up a bit so we can read it, and then if we need to move it down to see the graph, we will. Okay, find all the intervals in which the graph of f is concave down and also has a negative slope. So we want concave down and we want a negative slope. So we're looking for it to be concave down, so that's f double prime is what we need to examine, and a negative slope, we need to take a look at f prime. So I'm going to look and examine both the f prime and the f double prime number lines that I have created, and I am looking for when it's concave down and negative. So over here we had -5, then we had -3, 2, and 5. And I'm just right now copying down this f prime graph that I have right here, this number line. I'm going to just put it right back over here. So we ended up here with, from -5 to -3, we had positive values. Over here we had negatives, then we had negatives again. Now let's do the f double prime right underneath that one, and I'm just again going to copy this number line right under here so I can compare them both at the same time because it's a lot easier to do it that way. And this is at -4. Then we had -1, which will be right in there. Then we had 2, which is right here, and then we had 4, which would be right, put us right in that spot. And let's go ahead and indicate our regions over here. For -4, what I'll do is I will go ahead and I will create like a little border here so that you can understand I'm looking in each of these separate regions, and I've created that. So let's go ahead and indicate what we had for the -4 over here. We ended up with all of this being positive in this area, and from -4 to -1 we ended up with negatives in this area. Then we ended up with positives, and then we ended up with negatives here, and then back to positives. Okay, so I'm looking in the regions as we stated, and I want concave down, so I need F double prime to be negative. I want a negative slope, so I want F prime to be negative. So I'm looking at the spots where they are both negatives. And let's take a look at this, and we will see where we end up with both being negatives. Over here in this region, from here to here, both are negative. And then again, from here to here, both are negative. So I've got this region in here and this region in here, where I've got F prime and F double prime being negative, which means I've got a negative slope and it's concave down. So the answer for this ends up being from -3 to -1, union the interval 2 to 4, because both are negatives in this region for both the first derivative and the second derivative, because again, the first derivative tells me increasing, decreasing, so positive or negative slopes, and the second derivative tells me concavity, concave up, concave down. So, all right, now we're going to, let's move this up, and we are going to sketch a possible graph. Well, we've got a lot of information here, so we need to try to determine what possibly this looks like. So let's go ahead and start with something they gave us originally here in the problem. They told us right up above that f of -3 is 5. So let's go ahead and use that initial point that they gave us, and at -3 I've got a value of 5. So at f of -3 I'm going to move up to 5 and put a point right there. All right, now we do know certain things. We know that this only goes from -5 to 5, so I know I'm only going to be concerned with from here to here. I don't need to concern myself with anything past that in this graph. Then I know some concavity. I know that it's concave up and increasing all the way up to from -5 to -4. It's concave up and increasing. So let's go ahead and indicate that. Now again, it doesn't matter where we start here, we just need to make sure that we're concave up and increasing. I also know that I have a relative maximum at x equals -3. So this -3 value right there that we had indicated, I knew from this right here that it had that it was a relative maximum. So we can go ahead and start putting this curve together. I'm going to start somewhere along here, and I'm going to concave up, and I have a point of inflection, one other thing, at -4. So it changes concavity at -4. So this is going to go like this, and this is going to be like that. So we have some sort of concavity change here at -4. And again, I'm just guesstimating these values. I don't have more information to piece this together. I can piece it and make a great sketch by looking at what these possible values are, but we haven't learned that yet. We haven't learned how to take integrals and the area under the curve yet, so we're going to go ahead and bypass that portion right now because we're just doing a rough sketch. So then I know I'm going to go concave down from here and then all the way to my next inflection point, which is at -1. So at -1 I have another point of inflection, and this is where it changes that concavity from concave down, and we're going to be concave up all the way to 2, which is the other inflection point. So I will go ahead and put that somewhere right here, and I'll say that this is concave up like that. At -1 it changed that concavity. At 2 it's going to change that concavity. It's going to be concave down again, concave down to 4. So concave down to 4. And then it's going to end up being concave back up at that point, so we can go back up. Again, this is a rough sketch. It's a possible. I didn't examine the area under the curve to get a perfect sketch, but again, we don't know how to do that yet, so this is what we're going to stick with. All right, let's move on to the next problem. All right, so let's take a look at this next problem, and it says, find the x and y-intercepts and critical points in a relative extrema, intervals of increasing, decreasing, inflection points, and intervals of concavity for each. So again, let's remind ourselves, critical points, relative extrema, and intervals of increasing, decreasing is the first derivative. Inflection points and intervals of concavity is going to be the second derivative. So the first thing I want to do is let's go ahead and just start by finding the x-intercepts. So the x-intercepts for this one is we're going to set y equal to 0 and solve it. So we end up with 0 equaling x cubed times 4 minus 3x. So I'll get x equals 0 and 4/3. For the y-intercept, we're going to set x equal to 0 and solve it from there. So I end up with f of 0 is really what I'm looking for, and in this case I'll end up with 0. So this point is at 0, 0. You can find the coordinates for the other one if you choose. So we went ahead and did that. Now what I want to do for the first derivative is I could use the product rule, or I could just simply multiply this x cubed through, and I'll end up with 4x cubed minus 3x to the 4th, because now it's a little bit easier for me to take that first derivative. So the first derivative of this ends up being 12x squared minus 12x cubed. And the reason I'm taking the first derivative is for all this up here to help me find critical points, relative extrema, intervals of increasing and decreasing, and any inflection points, or I'm sorry, this inflection points and intervals concavity will be the second derivative. So setting this equal to 0 will give me my critical points. So I can take out a 12 and an x squared, and I'm left with 1 minus x equaling 0. So I end up with x equaling 0 and 1 as my two critical points. So we've done that. Now I need to determine if any of these are relative extrema, if they're maximums or minimums. How do I do that? Well, I can make a number line and see if they change intervals, the intervals change from increasing to decreasing. So I'm going to put 0 right there and put 1 right there, and I want to pick a value. This is f prime number line. I want to pick a value smaller than 0. So let's say f prime of -1. When I do that, I will get positive values here, anything less than 0. If I choose something between 0 and 1, let's say f prime of 1/2, I will get positive values again. And then if I choose something greater than 1, say f prime of 10, I will get negative values. So as you can see, there's only one spot where it changes from increasing to decreasing, and it's right here. It goes increasing. These slopes are positive because f prime tells me the slopes. They go to negative. So this tells me that I have a relative maximum at x equals 1. Well, if you wanted to find out the coordinate, just plug it back into the original equation, and you can get your coordinate of 1, 1. This will be my relative maximum. Okay, moving on to see increasing and decreasing. Since I have the first derivative on a number line here, I can find my intervals of increasing and decreasing. And let's see what these are. And for increasing, it's where it's positive. So we go from -infinity to 0, and we're going to union that from 0 to 1. Notice I did not include 0 because at that point it's neither positive nor negative. So we're just going to leave it alone for now. And since I do not know whether it's positive or negative, we don't include it. It's neither. That's the reason why. Okay, so for decreasing, we're going to end up where my slopes are negative. Okay, let's move on and find our inflection points and intervals of concavity. So we're going to slide this up, and for that we need the second derivative. So I will go ahead and use my first derivative that I had right here, and we will find what this ends up being, and this second derivative ends up being 24x minus 36x squared. So I get 0, set this equal to 0 to get your possible inflection points, and you get 2 minus 3x. So we get possible inflection points at x equals 0 and 2/3. How do I know if they are inflection points? Well, I need to test them on a number line. So we get our number line going here, and we have 2/3. Remember, this is an F double prime number line. So I test a value in here in this region for F double prime, say of -1. I will get negatives. Test one between 0 and 2/3, 1/3. I will get positives. Test values greater than 2/3, 10, 20, you'll get negatives again. Notice there is a sign change right here, so and right there. So that tells us those are points of inflection because it changes concavity. So my points of inflection, let's slide this up, my points of inflection, oops. So my inflection points are at x equals 0 and 2/3, because my change in concavity. Okay, so now we have our inflection points, and now just based on this and my graph, I can determine where it's concave up or down. We will say concave up in this region right in here, so this will be 0 to 2/3, and concave down and here and there, so it will be from -infinity to 0. We will union that with 2/3 to infinity. If you wanted to sketch a quick graph of this, let's go ahead and outline this. We can, because we have all the information that we need. We have where our X and Y intercepts are, we've got our relative maximum, we know where it's increasing, decreasing, we know our concavity and our inflection points, so we could do this real quick in a real rough sketch. It's going to go up, hit that inflection point, turn, go up, and then come back down. This is at 0, this is at 2/3, and this is my relative maximum at 1. Now let's go ahead and move on to the next problem here, and this time we're given f of x equals x plus 2 cosine x on the interval from 0 to 2 pi. So, going along with what we've done before, let's go ahead and first find the, let's use a different color here, let's go ahead and find the x and y intercepts. For the x-intercept, again, this is when 0 equals x plus 2 cosine x. This is for our x-intercepts. And in this case, this will not occur, because I'll end up with -x equaling 2 cosine x. Well, this never happens, so no x-intercept. Again, if we take a look at a unit circle here, we can see that we need to find a spot where -x and the cosine of x times 2 will be equal to each other. This will never happen. Okay, for the y-intercepts, we're going to do something similar, but this time we need f of 0. So in this case, we have f of 0. So we have 0 plus 2 cosine 0. Again, we are setting the x equal to 0. In this case, on the interval from 0 to 2 pi is all I'm concerned with. So I'll end up with this being 1, so this ends up being 0 plus 2, which is going to just end up being 2. So our y-intercept is at 2. Alright, so now let's find the critical points, relative extrema, intervals of increasing, decreasing. So I need my first derivative. So f prime of x is going to be 1 minus, again I'm taking the derivative here, 1 minus 2 sine x, because the derivative of cosine is negative sine. So working with this, I want to go ahead and set this equal to 0 to get my critical points. So we set this equal to 0, and I'll end up with 2 sine x equaling 1, the sine x equaling 1/2. So where does this happen? Well, I can go ahead and take a look at my unit circle, and over here at pi over 6, I'll get the coordinate root 3 over 2, comma 1/2. There's the sign. That's what I'm looking for. Again, another spot here would be at 5 pi over 6, where this occurs. So I want the sign to be positive 1/2. Those are my two values. So my critical points are at x equals pi over 6 and 5 pi over 6. So now let's take the next step, and we will put our critical points on a number line to determine if I have any relative extrema. So here is my number line. Let's go ahead and put pi over 6 here and 5 pi over 6 there. Remember, I only need from 0 to 2 pi. And I'm going to go ahead and test these, and over here I will get positive values. Over here I will get negative values. You could test a point such as pi over 2. Put it into your f prime of x. Again, this is an f prime of x. And over here I will get positives again. So from here we end up with a positive slope to a negative slope. The slope changes, so we go from increasing to decreasing. This is going to give me a relative maximum at x equals pi over 6, and over here I will have a negative slope to a positive slope, so this will be a relative minimum at x equals 5 pi over 6. Now, if you wanted the coordinates, you could say that this is pi over 6 and plug it back into the original f of pi over 6. It'll give you the coordinate. You can get 5 pi over 6 and then plug it back into the original f of 5 pi over 6, and it will give you, you can yield the y coordinate that goes with that. So since we've done that, let's go ahead and determine our intervals of increasing, decreasing. So increasing, when the slope is positive, I'll take a look at this right in here and right in there. So this is increasing from 0 to pi over 6, and we're going to union that with 5 pi over 6 to 2 pi. Again, feel free to put these in inequality form if you want. For decreasing, we're going to again take a look at what we have here, and I want the negative areas, so that occurs right in there. So it's decreasing from pi over 6 to 5 pi over 6. Those are the intervals of increasing and decreasing. Next step is we need to find the intervals of concavity and any inflection points. So doing that, we would need the second derivative. So f double prime of x would yield, in this case, a 0 right here, and then I would end up with negative 2 cosine x. So this was just negative 2 cosine x. Set this equal to 0 to get my possible points of inflection. Let's go ahead and slide this up. Set this equal to 0 to get my possible points of inflection, and this occurs when the cosine of x, I'm looking for this to be 0, basically, and this occurs at x equals pi over 2 and 3 pi over 2. Again, looking back at our unit circle from up here, we are looking for where the cosine is 0, that occurs right up there and right down there on my 0 to 2 pi interval. Alright, so got my possible inflection points. How do I know if they are inflection points? I will go ahead and test them on a number line again for f double prime, and I'll put my 2 points there. We've got pi over 2 and we've got 3 pi over 2. I will test intervals in between, pick a value in between, test them. Over here I'll end up with negatives, positives, and negatives. Again, what did I do? I tested, say, f of 0. I tested f of pi, double prime, and I tested f double prime of something greater than 3 pi over 2. You could say 2 pi if you want. Okay, so continuing on, so now I know that it changes right here, the concavity changes, and it does change right there. So I do know that both of them are points of inflection, so my inflection points are going to be at x equals pi over 2 and 3 pi over 2. If you wanted to know the y values that go on that, again, you would say pi over 2 and you plug it back into the original. And then you would say 3 pi over 2 and plug it back into the original f equation. Original right here, so that we know that that's how we're going to get the y value if we were asked to do that. So, moving on, since we have this, I can go ahead and determine where it's concave up and concave down. So, concave up is where the second derivative is positive, and that's going to occur on the interval from pi over 2 to 3 pi over 2. Concave down is where the second derivative is negative. That will occur from 0 to pi over 2. We will union that with 3 pi over 2 to 2 pi. Again, feel free to put those into interval notation if you choose to do so. I'm sorry, in inequality notation. If you wanted to sketch a quick graph of this, we have everything we need. We have over here, we have there is no X-intercept. We have our Y-intercept. We have critical points. We have intervals where it's increasing, decreasing, and intervals of concavity. So when you piece all this together, we know that we can go out to 2 pi over here. And here's pi. There's pi over 2. And there's 3 pi over 2. We know that we're going to have a relative maximum that occurs at pi over 6 and a relative minimum that occurs at 5 pi over 6. So at pi over 6 over here, I'm going to get a maximum. Relative minimum is going to occur right here at 5 pi over 6. And then at at 0, when x is 0, we start over up here at 2. So it'll go up, and then I have a point of inflection here at pi over 3, or I'm sorry, pi over 2. So that changes concavity. It'll be concave down in this region, concave up here, and then again at 3 pi over 2 it changes concavity again. So here's that's a possible sketch of this. We don't know, there's no relative maximum there, so let's just make sure our sketch continues on here. It changes concavity, but our sketch continues upward. Not sure if you could tell, but that is where it does change concavity again, but then it continues upward. So hopefully this video has been helpful for you. Please look for more videos, and good luck on your test.